Hello, happy last section of chapter 4. And it ain't easy being green, right?
Nope.
Yeah.
Nope.
Nope.
I got my Mount Magazine State Park shirt on today.
I've
And
got
you know what it says on the back?
what?
It says, you can't really see it, but it says, it's all good in the woods.
Oh my gosh. I'm gonna wear my UAM shirt because I believe in higher education and I support.
Well, I believe in nature.
Yeah, well, good for you. So, all right, let's jump in on this lesson about rational functions. A little word of warning: you might want to grab your calculator. Miss Young doesn't have a calculator. We learned that in the last video. I may have to mail her one, but so.
Maybe we can get Mr. Landry to let me borrow one.
Well, he is supposed to, have them for us, but whatever. Well,
I gave mine to my daughter. It's probably in her room in there somewhere, but that's scary.
Yeah, that's scary. It's only June, so it's not a big deal. You probably want one by the time we start school. But yeah, we recorded these all summer. I mean, like Miss Young and I have nothing better to do with our summers.
Ooh, overstating.
Yeah, well, I'm seeing all these.
Bobby has nothing to do with better to do with his summer. I, on the other hand, could be doing all the things. But yeah. I'm here with you because that's what I choose.
That's right. All right, so we're going to talk about rational functions today. And I'm trying to find a spot where we're not in the way, but our beautiful green is still available. A rational function is really just made up of the division of two polynomials. In the last section, we talked about the division. We had ones that came out evenly and ones that didn't. But basically, it's a polynomial divided by another polynomial. And the domain is all of the x values where the denominator doesn't equal 0. So what are we talking about again that we're always talking about?
Division by 0. Y'all can see my husband. How do you feel about division by 0, husband?
I don't like any kind of division.
He said he doesn't like any kind of division.
Fair enough, but we got to do it. So, all right. So like I said, this is a pretty calculator heavy intensive lesson, and the simplest rational function I can possibly think of is this guy right here. And I should probably put an X in there. And
so while we're discussing this, Mr. Bobby, why can't x over 1 be a rational function? Why is x over 1 or f of x equals x over 1? That's linear. Why is it not rational?
Well, I mean, and I guess in the strictest sense that it is, but it's really not going to have any interesting cases. I guess at 1 over x over 1 would still definitely technically meet the definition, but it's not going to have some of the properties that we're going to be looking for.
We tend to think about rational functions as having an x in the denominator because that's going to make weird stuff happen to the graph.
Yes, and if q of x was just a number, technically it meets but when we're just dividing by a constant, really we could default back to polynomials because all that would do is change the coefficients. So if q of x was 4, I would just take the polynomial on the top and divide everything by 4, okay?
Right.
All right, so let's look at the graph of 1 over x. And I've already entered this in, so if you're a calculator geek like me and have yours handy, grab it, make a new document, and type in 1 over x into your function entry line, and you should get
not a line.
Not a line. All right, I'm going to clear out of here because I want to. Now, what does this graph tell us other than it's pretty in pink?
So what's happening here is you're taking the number 1 and you're dividing it by all these real numbers. So 1 divided by 1 is 1, 1 divided by 2 is a half, 1 divided by 3 is a third, a fourth, a fifth, a sixth, a seventh, an eighth, and so on and so forth.
So as x gets bigger, the function value gets smaller.
Right. But actually, as you go to 0, like if you were to take 1 and divide it by a half, right, then you've got to keep change flip. So you would actually be doing 1 times 2. And so it actually gets bigger. 1 divided by a third would be 1 times 3. So that would be 3. So as you're approaching that 0, then your function is actually getting bigger. Now we don't usually think about graphs reading them that direction, but it's kind of important to understand here why you've got this, or I should say the nature of the graph around that y-axis.
So if I were to, right now I'm at 0.3, so if I were to go to 0.2, the graph would go higher. If I go to 0.1, it would get higher still. When I go to 0, I get womp womp.
Mr. Bobby,
Wow.
you can't divide by 0.
The calculator tells me that. It tells me that it's undefined, and it puts a little dotted line there. And that dotted line is not part of the graph. It's okay. But sometimes we'll draw that in there, and we call that an asymptote. Okay, it's a boundary line that kind of limits the graph, that doesn't allow me to get, I'm going to get close to that line, but it's not there. Okay.
In another sense, you would call this a domain restriction because it can't be part of the domain, right? You can see this graph goes left forever and it goes right forever, but it's undefined as 0.
And that's what we're saying right here, that wherever the bottom polynomial is equal to 0, that is not part of the domain. So for this function that we're looking at right now, we would say the domain is all real numbers except 0. Okay? So let's look at a slightly different graph here. So I'm going to hit another one in here and do, we said 1 divided by x squared maybe.
So what I would expect to happen now is all those negatives on the left side of the graph underneath the x-axis, we're going to square those. So we should expect to see them pop up into the positives.
And that's what happened. And it's a little steeper because when we square numbers, they get numbers bigger than 1, they get bigger. And so that makes sense. Okay. Now that asymptote is also again at 0, because if I put 0 in and square it, it's still 0. But let's look at one more rational function that's a little more interesting. Give me your favorite number between 1 and, I don't know, 6.
3.
Okay, x minus 3.
Now, guys, what we're doing here is a transformation on, can you hide the f5, 1 over x squared? Just hide that.
And the graph.
So we took 1 over x and we subtracted 3 inside that fraction. So what we're really doing here is just a transformation on x. So minus 3 is going to shift it right 3 because it's opposite because it's inside. So you took that vertical asymptote that was at 0 and it shifts with the graph, right? The whole vertical. Now, if I moved it up or down, that wouldn't shift that asymptote. But because I'm shifting it left and right, and I've just used the word that we haven't taught them yet, but the restriction at 0 gets shifted. So on F6, you're going to see it approaching from this, using calculus words. I shouldn't use calculus words, or should I? What do you think? You know, sometimes on the ACT, you'll see as, for this particular function, as x approaches some number, what does y approach? That actually does get asked sometimes. So you can see as x approaches 3 from either direction, right? Well,
yeah.
It's, you know, the function's going really high up or the function's going really low down. So, you know, you've got that same restriction happening there. I just talked in circles. I'm gonna let you take over.
Yeah, okay. So basically we're doing that same stuff we did with functions before. We're translating or shifting the graph. We shifted it right. And Ms. Young likes to say shifts happen, so.
I thought we weren't saying that.
Well, you're the one who was saying it, not me, so I didn't say it. All right, so anyway, moving on, let's look at when, that kind of gave you a sense of the basic, hopefully, gave you a sense of the basic parent graph, but there's going to be a lot of craziness that can happen with these guys. So let's look at one that's a little bit more interesting. So here's a graph, or here's a function x minus 3 over x squared minus 4. And what we want to do is begin by finding those domains. And again, the domain is where the denominator isn't equal to 0. So I just need to find those offensive points and then say, you guys go away. Okay, so let's find the denominators zeros. So I'm going to take x squared minus 4. I think I know how to do this one. That's going to give me x is equal to plus or minus 2, right?
So remember, guys, we're actually saying in this function, x squared minus 4 can't be 0. And so he's figuring
Those are bad numbers.
bad twos.
Bad 2, bad negative 2. So how do I want you to report your answer? Those are the bad numbers, okay? Sometimes, like, everybody else is cool, but these two dudes just don't play nice with everything, okay? So what we would say, how do you want interval notation, or you want real numbers except?
I mean, I think you could do it either way. Like, the easy way to say it would be using the all real number symbol, and then comma x cannot equal plus or minus 2. So it's kind of the easy way to do it, is say, you know, in this domain, every number is okay except plus or minus 2. We could do it that way. We can also do an interval notation. So, you know, if it were all real numbers, it would be every number from negative infinity to positive infinity. But if we want to leave out these two numbers, we would say every number from negative infinity to negative 2, but not including negative 2. So we're going to use a parentheses. Every number from negative 2 to 2, but not including negative 2 and 2. So we're going to use parentheses. And then every number from 2 to positive infinity, but not including 2. So we're going to use parentheses. Now he's using commas between those intervals.
Yeah.
Actual interval notation would have you use what's called a union symbol. I'm only bringing this up because I'm not sure if ACT ever uses that symbol, but if they did, just so you see it,
yeah, that
just joins together intervals of numbers.
And again, I'm not sure what you might run into in different classes, so
right.
That's why we're covering our bases. So yeah, fair enough. All right, let's look at this graph on the calculator.
Please, let's do.
All right, so when I go over
Whoa.
What, you don't like all the writing on top of the graph?
Too much happening.
Okay, all right. So this is the graph of that function, except our faces are over top of it.
I thought that rational functions had one vertical missing piece.
Well, we had one because there was only one place in those problems before where the denominator equaled to 0. But here we found 2 places. So every place where you have the denominator equals 0, you're going to have some funny business going on. Okay.
Funny business.
Funny business is what we're calling it. Well, and it's not always what you think in terms of funny business. I was very deliberate on my choice of words there. So when we think there's something weird going on at 2, and I can see there's an undefined point at 2, and there's an asymptote there. And if I go to negative 2, there's another funny point, and there's another asymptote there. Okay?
I like to say that these vertical asymptotes like bend the graph.
Okay, they're kind of like boundary lines, or anybody ever have an electric fence for their dog and you shock the dog, you can't cross the line, it's gonna,
Yikes, why are we talking?
Yeah, people do that, I
know.
I have a fence. I have a wooden fence back there. My dogs don't get shocked, all right? But, it's kind of like that too, which is awkward. All right, let's not be awkward anymore.
So maybe we should tell them where the vertical asymptotes are coming from then.
Well, that's what you made me erase ago. When that denominator, the denominator is 0, those numbers right here, these guys told me that x is equal to -2 or plus or minus 2, or actually can't be equal to plus or minus 2. So wherever that denominator was equal to 0, we got that what I was calling funny business, and the first funny business we've seen is a asymptote. But there's other funny business.
Yeah, there is. But I just wanted you to see, we're going to talk about vertical asymptotes, and as you can see here now, An asymptote is a line that the graph approaches but never touches. And so we're going to find those vertical asymptotes by setting the denominator equal to 0 and solving it.
Except when we aren't. All right, here's one. I changed a slight change to the equation. It was x minus 3 at first. Now it's x minus 2.
Yeah, so just change that numerator by one number.
Okay, and that's fine. The funny points, the badness, something's gonna happen at 2 and negative 2 again. Nothing's changed there, right?
Right. So if same exact algebra problem, like set the denominator equal to 0, you get plus or minus 2. And now I know what you're thinking. You're thinking this is also going to have two vertical asymptotes, one at 2 and one at negative 2. Got to. Same denominator. And you just told me that that's where the vertical asymptotes come from. So let's graph it.
All right, so let me.
Mr. Bobby.
All right.
I got it figured out.
All right, so here's the graph of this new, well, that's the graph of the last one. Here's the graph of the new one.
What?
All right.
So I see my vertical asymptote at negative 2.
So, all right, give me a second to trace over to the negative 2 and see what's going on here. All right, so there's my vertical asymptote. I'm cool there. But
I should have another vertical asymptote at 2.
Well, I ain't got no vertical asymptote. I mean, like you can see right here, it's just nice and smooth. This looks
looks like there's a point there. So let's figure out what that point is and why all of a sudden we can divide by 0.
Okay, so if I go over to 2, oh, your face is obscuring it. I put you right over in the bottom corner. Now, wait a second. That's like an asymptote, but not really an asymptote.
Right, so it still says undefined like an asymptote would, but it doesn't bend the graph.
Why? So what is happening at 2 is what would happen if I factored the denominator? I would get
x plus 2, x minus 2.
X plus 2, x minus 2. So I'm going to try to cram this down here. X minus 2 on top. And then I'm going to have x plus 2. And then x minus 2. That's interesting.
So I see a like term on top and a like term on bottom, and you can divide anything by itself.
Right.
Pow!
But
And
when
it
you
becomes
divide
1.
by itself, and that would be 1, you got to be careful. That works for everything in the whole world except for one thing. It works for every number value of x except 2. Because what you're doing is you're dividing out 0. And you're dividing by 0 again. So what you really have on the graph here is we have a hole in the graph. There's like one little gap at x equals 2. And the calculator doesn't pick it up because your calculator plots a whole bunch of points, connects the dots. And there may be a hole there. There is. You just can't see it because it's so small and your eyes aren't so good. Maybe you need some bifocals. Want my glasses? Glasses. You can't see it because you can't see one point, like you can't see an atom. Okay? So there's actually, the calculator doesn't do a good job of this is where you need your brain and you have to have a little bit of smarts. Okay? Yeah. This one has an asymptote, right? We can say there's that boundary line, whatever sometimes we'll do it with like a dotted line just to kind of help us frame and sketch the graph. You don't really have to have that's really not part of the graph, but if you do draw those vertical asymptotes in as like a dotted line, we can.
Does removable have an E in it?
Yes.
So I just misspelled that?
That's okay, I think. I don't know. In later courses, you might hear these as referred to as removable and non-removable discontinuities.
Right. And I bring it up simply because I do think it kind of helps you differentiate in your mind which one's which, right? Because if you can remove the factor, then it's removable and it's a hole in the graph. If it's non-removable, meaning you've simplified it as far as it will go, and it is still in the problem, it is non-removable and it's a vertical asymptote.
And so, and I always think of that as like the hole behind the door. Like, you ever have like a hole in your plaster on the door where the door hits it?
And maybe it's happened before.
Yeah, maybe it's happened before. You open the door too hard and it makes a hole in the drywall, but you can spackle over that. And it's a hole. Yeah, you can.
The calculator spackling our hole. Is that what you're saying?
The calculator is spackling our hole, and we can cover it over. but I can't fix like, something that doesn't connect like that. So anyway, all right, that's sometimes stupid too, but that helps me remember it. All right, let's go back to what our whole point was anyway. All right, so there's two kinds of funny business that can happen with a rational function. You can get a hole in the graph and an asymptote, okay? And the hole in the graph basically comes when you divide it away. Now, let's look at a whole bunch of them and try to find where the vertical asymptotes might be if we were able to divide it out. So how about we try to do some factoring, okay? So let's look at g of x. Can I factor the numerator at all? Nope, good, okay. So let me try to factor that denominator and see what are the factors of x squared minus 3x minus 4. So I'm just gonna go off.
-4 and +1.
Oh, x minus 3. No, dang it. You already factored it, so let me clear that out. And just do it. So it's gonna be x minus 4 and x plus 1. Is that what you said?
Yep.
Right. So what are the problem children there? This is going to give me x cannot equal 4. And this is going to give me x cannot equal -1. Those are my asymptotes, 4 and -1.
And both of them are non-removable because neither of them would divide out with 5x minus 3, making both of them vertical asymptotes.
Okay. So problem h of x the top does factor. I can factor out an x, can't I? I have a GCF of x.
You can.
And that's going to give me 6x squared minus 5.
Mm-hmm.
That ain't going nowhere. Right? And
I don't believe so.
No. And then the bottom, I'm going to get, let's see here. I can take a 2x out, right?
Yep.
And when I take a 2x out of that, I'm going to have x squared minus 9, right?
X squared minus 9.
Yeah, but I know what that is, don't I? I know that's going to be x plus 3, x minus 3.
Yep.
I'm going to have room in there, x minus 3.
Now remember that instructions here say determine vertical asymptotes.
Yeah.
So we only want to look at those non-removable restrictions. So is there anything we can remove at this point, Mr. Bobby? And he's going straight to the answers here.
Yeah, I was going to go straight to the answer. X cannot equal -3, or x cannot equal to, what can I, go ahead, well, you answer it since you're the one who brought it up. I could take.
You might be tempted to say that x equals 0 is also a vertical asymptote, but it's removable because x divided by x is 1. And so we know there's some funny business happening at x equals 0, but it turns out that that's just a hole in the graph. It's not a vertical asymptote.
Okay, we can remove x equals 0. So that's not one of our answers. So -3 and 3 are our only answers.
Right.
Only asymptotes.
Right.
Okay. What about k of x?
Well, I'm going to ignore the numerator for just a second because she's ugly. And also, I'm looking down here because that's where I would look for a vertical asymptote anyways. And I'm thinking to myself, I want to try to factor x squared plus 3, but it's not the difference of squares, it's a sum. So if I think about solving that, I would get x squared is equal to -1, take the square root. Right, because this is going to give me an imaginary unit. So I don't even have to worry about the numerator in this problem because right off the bat, there are no real solutions to the denominator. So there are no real restrictions to the denominator or to this problem.
Okay. So, and I could, if you want to confirm, you can graph each one of these in your calculator, and you might want to do that to see what they look like just to help make sense of it and see that we are hopefully on the right track. We're not going to because
The video would be 8 years
It
long.
would be 80 hours long, and nobody wants that. So, okay. So let's do something else with this graph that we had a moment ago. What I want to do now, instead of focusing on what happens in the middle, is I want to focus what happens out on the ends. Okay, as we go out to the very, very, very small numbers and the very, very big numbers on the ends. What's happening? X minus 3 over x squared minus 4. So let's go back to the calculator for a moment. And I think I had that on this page, right?
Mm-hmm.
So I'm already still tracing on it, which is nice. That was nice of me. So what happens to this graph? And I'm going to scoot on out to the right. And Miss Young's just going to.
Let's go to like 100. X equals 100.
Well, all right. I'm going to get there. I'm going.
You just want to slowly.
I just want to slowly walk out to 100.
This is gonna be the longest video ever.
Okay, so I'll just type in 100. It's 0.01.
What about 1,000?
Okay, now it's 9.97 e negative 4, which got bigger.
Yeah. No.
But that's a bigger number than 0.01.
Hi, welcome to scientific notation. This is point
Oh.
0.000997.
Oh, okay. When I saw the 9, I thought it was bigger.
How about 10,000?
Now it's got smaller again because that 1 is less than 9, but I have more negatives. I'm getting this y value is getting more. It's not scientific notation. It's a decimal point and a bunch of zeros.
Yeah.
And look at that negative 4. Let's see what happens when I go out to 1 million. It went up to -6, so I have more zeros on my decimal. It keeps getting closer and closer to 0, but it's not quite getting there. All right. So
Guess what it's never going to get to?
it's probably not getting to 0 unless I
It's never going to get to 0.
I mean, now like I can probably freak my calculator out and like make it have so many zeros that the calculator can't handle it because technology can't conceive of things like this as well as we can. But if I have 1 or a small number divided by a really, really, really big number, it's going to keep getting closer and closer to 0, but never there.
So worthy of conversation, if we go back to that parent function, like the simplest function and the function or whatever, what he's saying is like, I want to try to make this 0. Go ahead, Mr. Bobby, solve it.
That's not fair. That's not nice. Because if I multiply both sides of the equation by x, I'm going to get a problem. All right. And this is also why, if I multiply both sides by x, I'm going to get 1 equals to, I was trying to do it too, 1 equals to 0. And that
Yeah, that makes sense.
That don't feel right.
That doesn't feel right.
That's not,
Because it's not possible.
it's not going to happen. So that's why another reason why you can't divide by 0. Oh my gosh, I'm so sick of saying, they're probably sick of us saying that too.
Yeah.
Okay, so what the point is this guy has what we call a horizontal asymptote, okay? And the horizontal asymptote is the x-axis, all right? Just like a vertical asymptote was the line that we're approaching. Now, we're approaching this on the ends. I don't care about what's going on in the middle. We can have some silliness in the middle. But on the big values out on this side and this side, we're getting closer and closer to the horizontal asymptote. In between, who knows what's going on? It's kind of feels like the polynomial thing, okay?
Yeah.
So let's kind of summarize what we mean about this with horizontal asymptotes. So rational functions have 2 different types of asymptotes. They'll have vertical asymptotes where the denominator is equal to 0. But some of them will also have horizontal asymptotes, and that has to do, again, with the degrees of each of the pieces. So if the degree of the numerator is less than the degree of the denominator, so if the bottom has a bigger exponent, which is what it was in the last problem, the x-axis is the asymptote, okay? So this is the fat bottom rational function, okay? Well, you gotta go to the cupcake shop, flat down, it's like, if it's bigger on the bottom, it's gotta sit on the axis. Okay. What?
Nothing.
Okay.
Mr. Bobby just made himself blush, I think.
You guys need to go get a cupcake now. If the degrees are equal, then all you're going to do is go to the leading coefficients. So if it's got like x squared on the top and x squared in the bottom, those x squareds would kind of divide out, and you just grab the leading coefficients. Everything else is going to is going to be blown away by the bigger power. Okay, if the degree of the numerator is bigger than the degree of the bottom, then it's not going to have a horizontal asymptote at all. It's going to have what we call an oblique asymptote. Sometimes they're called slant asymptotes. Okay, so if it's got a bigger exponent on the numerator, you ain't got none. It's really actually a lot easier than what we're saying, and it's, you know.
Yeah. We'll kind of walk you through it. There, you've got three options here. It's going to be bottom heavy, it's going to be balanced, or it's going to be top heavy. And the way you're going to decide that is by looking and comparing the exponents, or the degree of the numerator and the degree of the denominator.
And that was like super easy earlier on to do it for one. We're just going to do it for two, and we didn't compare. I think y'all can handle this. Trust me. So let's try it. So let's look at g of x. Is that the exponent on the bigger on the top or the bigger on the bottom?
So one on the top, two on the bottom, bigger on the bottom,
So
which
that,
means it's
this
fat
is,
bottom, which means it's going to sit on the x-axis.
okay. So okay, that's our horizontal asymptote, and I'm going to see if I can move this over.
Yeah. Also, you could also write y equals 0 if you would like to for your horizontal asymptote.
Okay. All right. So and that's all you got to do. You just got to compare them. Like, you don't have to prove it to us. Okay. I think you can do that. Now, the second problem, h of x. I have a 3 exponent in the numerator, a 3 exponent in the denominator. Those x cubes are going to balance each other out. And the rest of this junk over here is going to get, like, you're just going to ignore this. Because for bigger and bigger values, if I take a really, really big number and cube it, it's going to be huge compared to taking that really, really big number and multiplying by 5. Okay? So it's going to dominate for really, really big numbers when you cube it. So when I look at that, all I'm going to focus on is the 6 and the 2. So my horizontal asymptote is going to be at y equals 6 divided by 2. But what's 6 divided by 2? Which is 3. Okay.
Now remember, we're talking about a horizontal asymptote. So what just happened is where it was on the x-axis, it got shifted up 3.
Okay. And then what about, what about this guy down here? It's bigger on the top. And this is one that this would have no horizontal asymptote, because this is what's going to be called a slant asymptote. We'll look at this in a minute. Okay. Can't spell, whatever. All right, so moving on to, let's look at, just for the sake of completeness and prettiness, what it would look like.
So you can, he's about to graph this. There is a way to algebraically find this, like he's about to type it in for you. But you can see this, like, instead of it approaching horizontally, it looks like the whole thing's been tilted, and now it's got this like diagonal line that it's kind of following.
And if you actually remember that a fraction is really a division. So if I were to actually do the long division like we did in the previous section and ignore the remainder, you would get, I'm not going to ask you to do this, but it's just kind of fun for those of us who are geeks. I would do x, I said it was -2 a minute ago.
Yeah, I think -2.
If I were to do the actual long division, x minus 2 is what you would get as your quotient without the remainder. That is what's called a slant asymptote or an oblique asymptote. I'm not going to quiz you on that.
Right.
So don't worry about it, but it's just kind of mathematically neat.
And
Okay?
it turns out for every single one of those that you could divide, but we're just giving you the shortcut on how to find those horizontal asymptotes pretty quickly.
Wait. We make them do it the long way first.
No.
Like, aren't we supposed to? Isn't that part of being a math teacher? Is make them do it the hard way and then maybe
No.
show them the short way?
No.
I thought that was a rule.
Mm-mm.
Math teachers.
We're not doing it.
Okay. Well, we just won't tell anybody. Okay. They don't have any proof. All right. So let's sketch a graph of this guy and put it all together. So what do we know about the asymptotes? Well, we've already seen this as a denominator before, right? We've seen asymptotes at -2 and +2. So
Yeah.
she's going to do the math for me maybe a little bit.
Well, I'm just gonna write. So, and then you can do the graph. So we've already done this twice. So we've got vertical asymptotes at x equals -2 and x equals +2 because neither of those factors are going to divide out with x minus 8.
Okay. What about
That means we have no holes in the graph.
no hole? Okay. What about the horizontal asymptote? Is this top heavy, balanced, or bottom heavy?
This is bottom heavy because it's 1/2. Degrees are 1/2.
And bottom heavy means that the x-axis is an asymptote. Okay. Now I'm asked to find the intercepts. So how am I going to find the?
Start with y. So if I want to find a y-intercept, that means I'm going to make x 0. So I would just kind of quickly do the math here. I would do 0 minus 8 over 0 minus 4.
And that would be -8 divided by -4, which is +2.
Mm-hmm. So we would have a y-intercept at 0, 2.
Okay. And then what about to find the x-intercepts, we have to set that expression, the function equal to 0.
Mm-hmm.
And so when I have, you want me to
I'm
help?
going to let you do that part because you can write a little faster than me.
Yeah, so if I do x minus 8 over x squared minus 4 equal to 0, when we do this, the only way to make a fraction equal to 0 is to make the numerator equal to 0, right? So really this is going to have, I would multiply both sides by x squared minus 4 and it would go away. So that would tell me x equals 8. So I would have the point 8, 0 here. Well, wait a second. I got a real problem with this, Miss Young. I'm going to put a dot here.
I
And
dislike it.
I dislike it because you said I couldn't have and you said an asymptote's a line I couldn't touch, and I just touched it.
So remember, guys, with horizontal asymptotes, we're talking about end behavior of the function. So we're not talking about what's happening right in the middle. Can we cross the horizontal asymptote? We absolutely can, because we're talking about what happens when x gets really big. Like, what is it at 10,000? What is it a million? And really small, like -10,000 or -1 million. If it crosses at 8, who cares? Because it's end behavior.
Yep. So an asymptote is a line that determines behavior for the end. A horizontal asymptote's at the end. So
Yeah.
now I just got to figure out, like, I know right in here, this graph is going to go like this because I have a positive number at 2 and I don't have it. It's never going to cross the x-axis. So I got to follow those bendy lines.
It is going to cross the x-axis, but only at 8.
Only at 8. I would have already found another x-axis intercept. So what I need to do is figure out where it is. Like, that point right here is the only place I can cross the x-axis. So I'm either going to come to the right of 2. I'm going to come up and through that point and back down to the asymptote, or go the other way. So let me pick a number like 4. If I put 4 into my function, is it going to be positive or negative, Ms. Young?
Well, we're going to do 4 minus 8 over 4 squared, which is 16 minus 4.
And I'm going to get -4 on the top and 12 on the bottom, right?
Yep, -4/12.
So that would be 1/3.
Yeah. Negative style.
Or negative 12. Yeah, negative 12. So negative 1/3. So my point would be like right there. Right? So
Means
that's
I'm
also
gonna have
everywhere between 2 and 8, it's below the x-axis. So I got to come along this asymptote down here. I'm going to come up. Oops, sorry.
Whoa.
Back,
Whoa.
back too far. I'm going to go down here, and I'm going to come up, hit this point, come up, and then back down to the asymptote. Okay? Then I need to test the other side. I'm going to pick like -4. So if I put a negative here, that would be negative. That would make this negative 12. And that would give me -1. So at -4, -1 would be that point right there. Ooh, back up. -1 there. So I would have a point right there. And I'm never going to cross the x-axis. So using my bendy lines.
Yeah.
I have
Approach both asymptotes, both the vertical and the horizontal.
Now that's a really crummy graph. I know my artistic abilities are limited, but if I were to, I would be able to plug this into my calculator and confirm the answers that I've gotten if I wanted to, okay?
Yep.
All right, so we'll clear all that out. And I think,
Now, guys, we know we're going to ask you to graph up and you're going to have a calculator, but you do need to have a method to finding it. So like the expectation here is we might say graph this rational function, show your work. So you would need to show each piece of like coming to or explaining how did you get that vertical asymptote, that horizontal asymptote. Like you would need to explain balanced and then 6 divided by 3 or bottom heavy y = 0. So there needs to be you need to be able to explain why the calculator looks the way that it does.
that's exactly what we care about as much as anything. So we're definitely going to do that. So thank you. And I hope you have a wonderful rest of your day. And I think we're good to go.
Bye, you guys.
Wow.